let's jump into it. So thank you for the intro, Murat. I think that mostly covers it. Just one thing, like you kind of talked about. At C3, I'm working a lot on LLMs these days, specifically creating what, I mean, people just know it maybe as like co-pilots, coding assistant tools, other LLM-based tools to, solve coding questions, help developers be more proficient in a given coding language. And that actually involves, taking some base models. Maybe if you're following, you've heard of like Llama or Microsoft's Phi or some other things, and actually fine-tuning them, pre-training them, really understanding how do you take an LLM, generally that you will port over from an AI lab, like they've done a good job creating a pre-trained version, and then continuing to fine-tune it for your use case. So yeah, somebody asked the question, perfect. Type answer. Okay, so I asked, I shared the notebook in the chat. And also there's a QA now with the link of the notebook. I just remember that from previous sessions because I know people join later and they want access to the notebook. So this is going to be very hands-on, or at least I'd like it to be. I always want it to be hands-on, and I want everyone to come away with something that they built. Let's jump into this. Unfortunately, I couldn't figure out how to make my second monitor work today. It was not behaving well. So if I don't see questions in the chat, I apologize. I'm just not able to keep up with it right now, but maybe like raise a hand and I'll try and cover them. So this is just like a notebook. And if you were in the previous session, I also kind of went over this. There's a lot of depth in understanding like the latest of LLM development. How do we go from text and strings to something like a GPT 4.0 or an o1 that demonstrates like unbelievably, just amazing capabilities and performance. And for the notebook, so again, like a high level summary. Yeah. So I think this is basically covering the summary right here, right? We're going to look at the building blocks of LLMs, right? Specifically understanding things like tokenization, embeddings. And then that's kind of the core of NLP. Like you need to know tokenization and embeddings to really understand the latest and greatest in all things natural language processing. And then from there, okay, I want to quickly do an overview of how, transformers are working, transformer being the technology behind these LLMs, something like attention, and just quick walkthroughs of what is attention, how do we compute it. A kind of trivial, very trivial, it's like a toy example, but it helps illustrate the concepts of maybe making our own LLM, which is usually mixing like transformers and typical like neural networks, multi-layer perceptrons. And then the coolest part, probably, because it's the most hands-on part, it's not theoretical. Let's like look at how do we actually fine-tune LLMs today. And even though it's at the end, I'm going to start with this because it just makes things like tangible. We're going to see it right now. If you click on either one of these, maybe I would recommend SFT for LLMs. There's a lot of frameworks for machine learning engineers, data scientists to develop LLMs, right? PyTorch, Hugging Face. And then lately there's one called Unsloth, which I use a lot, and it has a ton of popularity because they've just made it, I think, even easier at an interface and framework level and more memory efficient. They're like known for their memory efficiency. Also, by the way, I should maybe ask some questions in the chat will be the best way to go about, just so I can kind of weave in my answers. I am able to see the chat questions, which I thought I wasn't going to be able to, but turns out I am. So we can stick with that. Oh, I just found a typo here. I can fix that. So This is their GitHub. It's an open source repo. This is not some proprietary technology. You can see everything that they work on, and they're constantly updating to support the latest models, like Llama 3.2 that's come out, Phi, Quen, Google's Gemma, so on and so on and so on. And they have like a ton of notebooks, which is what we're going to jump into right now for training LLMs. So actually, let's start with that. Let's click on this link if you have this notebook. Show the recording for the session. Yeah, so for people who just joined, the link to this notebook is actually in the answered question and answer. If you look at the Q&A and you look at answered, I'm linking to this notebook that I'm sharing. If for whatever reason that doesn't work, let me know, but it should work. And once again, Q&A will have the notebook. So at the bottom of this shared notebook, and by the way, feel free to, because I've given only people view permission, feel free to like make a copy or save a copy, and that lets you run it on your own. For these notebooks that are linked here, if you click this, it'll open up something that looks like this. This is from Unsloth. This is let's go fine tune our own LLM for our own use case. Okay. What you'll see is a ton of available models from Unsloth and from Hugging Face, which just stores these models. We're gonna pick today Meta Llama 3.1 8B Instruct. I'm curious how many people in the chat like understand what this means. Like, what is an instruct model? What does 8B mean? Okay, 3.1 is just a version, so fine. But let me know. I mean, I want to have an idea of what background people are coming in with. And this is it. This is loading an LLM into our notebook. Unsloth actually gives you free access to a T4 GPU to go and experiment with the library. So everyone can actually just have a local cloud, but local LLM. And this is it. This is the model. Just for context, you might ask the question of, you might want to get some more information on this model. They're always available on Hugging Face, so we can take a look. I mean, what can we learn about Llama 3.1 8B? There's a model card, there's information about it, but really the thing I wanted to share, they'll also, by the way, give you like starter code. At least in this case, they're asking you to use transformers, which is fine. That's a viable framework. To basically be able to do inference right away. What you can also ask is, how good is this model? And they actually provide a little bit of a table here. There's a lot of benchmarks out there that people are using to ballpark estimate how strong is an LLM. So there's categories like general knowledge and these benchmark data sets that kind of the industry has accepted, like MMLU, which is basically multiple choice questions around general knowledge. And then each column here is a different model and how it's performing on this benchmark data set. And you can see these data sets, they're all open source. The beauty of this field is almost everything is open source. So, you could go to a bigger model, which would be Llama 3.1 405B. That means it has 405 billion parameters. For context, something like a GPT-4 has roughly 1 trillion parameters. So these are like, frontier models, top of the line performance. You can see that a model that is like almost 1/100th the size in 3.1 8B versus 405B, still, relatively speaking, gets pretty good performance across these benchmarks compared to something that is much higher capacity. And comparatively, like training an 8B model compared to a 405B model is night and day in terms of resources required and time. But it's still performant, gets pretty good results on being able to code, on reasoning, on math, tool usage, and so on and so on. So I see a question, instruct meeting instructions. Yes. So just to cover it, and it would be part of the actual course. There's no way to cover all of, I guess, LLMs in like 1 hour, but I'm going to try and give the fire hose approach. How are these LLMs created? Basically, you start with, if you can imagine, it's just next token prediction, funny enough, which you can, if you're not familiar with tokens, it's next word. We simply optimize the model to be better and better at predicting the next token in a sequence conditioned on all the previous tokens that came before it. That is it. That is what we call pre-training. It's teacher forcing training. And that's where you'll hear that these AI labs use like the entire internet, which is trillions and trillions of tokens and words to basically somehow get these models to understand how to speak English, speak other languages, how to actually seem to conversate reasonably. Again, we call that pre-training. Or in this notebook, I actually, if you want to do CPT, which continued pre-training, that's the goal. But if you want these models to start behaving like assistants and start behaving conversationally, you typically do something called instruction fine-tuning or supervised fine-tuning, where you're actually giving question answer examples. And you're expecting the model still to, it's just predicting the next token, but conditioned on a given question and what the answer should be. This may or may not make sense. This may or may not seem like magic. Honestly, even when you build an understanding for the math and the technology under the hood, it's still kind of magical that it works so well, but it does. Again, we would spend more time on that, but I don't want to go too deep since we have a lot of things to cover. Another magical thing is really, if you don't know already, these models are just matrices of numbers. It's, in this case, 8 billion parameters, 8 billion floating point numbers. That's it. 8 billion floating point numbers somehow put together in an intelligent way and chosen successfully gets you like GPT-4, which is kind of crazy. And if you load the model in Unsloth, you can actually see all the layers in this model because they're composed of various layers, right? So if you look at just this printed out output, which may or may not be easy to go through, just run this again. For some reason, I'm not able to actually scroll through this, which fine. But you have embedding layers, you have attention layers, you actually have multi-layer perceptron layers, and so on and so on and so on. And you can actually access these. Maybe I can try. I think it's state dict keys. Yeah, so let's do this. You can actually go and access one of these layers. Is that not correct? State dict. Honestly, I'm just going to try on the fly right now. It's not subscriptable. Ah, I see. So this is some type that I can't really go through. Well, point is, I mean, again, we don't need to spend too much time into it, but you can actually see what all the weights are. They're all here. Not to spend too much time onto that. There's other techniques, by the way, when training these LLMs, which is called parameter efficient techniques. Okay, a common one is LoRa. Basically, in this model, you have 8 billion parameters. And if you want to train this model, one approach is to train all 8 billion parameters. But as these models get larger, that's pretty compute intensive. Like you need beefy GPUs to be able to hold these 8 billion parameters. And then when you train, you actually need multiple copies of them just to do like the backward pass, back propagation, update all the parameters. Instead, what we figured out is you can actually use a subset of the number of parameters available through a technique called like low rank adapters, which again, I could spend the whole class on, but just know that you can do it. It's basically a way to add regularization so you don't maybe overfit on your new data set. and also just make the training more compute friendly. We can just load this with Unsloth through their libraries, super easy. We'll get this model now with like the LoRa applied to it. And then you can add your own data set. Again, won't spend too much time here, but you can download data sets online, or you could use your own. In this case, let's just try this one. This is available on Hugging Face, so this actually corresponds to a Hugging Face repo. Now we can see, what's in this data set. Maybe I'll just get the first element. Okay. You're going to see kind of the overhead, and we don't need to get into the details of the data model and the structuring that LLMs expect. But this is an example of a human question where, explain what Boolean operators are, what they do, blah, 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 blah. And then what the answer should be based on this data set. And, pretty lengthy answer. This is what we're teaching the model. And we have 100,000 examples of this. You'll see this conversational formatting, and it does mean something. But for now, let's not worry about it. We can kind of map, and let me take some time while this loads. Okay, so link to the notebook. If you look at the Q&A and the answered Q&A, this notebook is linked, or the original notebook is linked. And then at the end, the original link actually points to, let me put this out of the way. Recording is actually going on YouTube as well. The original notebook will link here. We're going to walk through some transformers building blocks, but at the end, and actually I'm starting with the end because it's kind of like it's the thing you can really take away from this. Let's fine tune our own LLM. So open this notebook from this framework called Unsloth. It'll take you here. You just run the notebook and you can fine tune your own LLM, which is exactly what we're doing here. We've kind of covered loading it, what an LLM is composed of, blah, 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 blah. Long story short, would it surprise you to see that, let's look at the 5th index here. The conversation is in this format of, well, I guess it's kind of gone away. Let's do it here. Right, a question coming from a user, how do astronomers determine the original wavelength of light, blah, blah, blah. Okay, and this is what the answer should be. What we actually passed to the LLM to learn is this. This is the full text that goes to the LLM. What you're seeing is kind of the guts of how LLMs become conversational, because typically, like if you look at in the history of these things like GPT-3 and GPT-2 and whatnot, they could generate sequences that make sense, but they weren't really good at following instructions, understanding how to be like a useful conversational assistant. One way that's resolved is by actually doing this fine tuning. And it's kind of like hard coding, that's at least the way I think about it. It's hard coding roles in a conversation. So you're using this like very esoteric format of like end of turn ID, start header ID, end header ID to basically bold signpost to the LLM. Hey, the user is talking right now. This is everything after this is the user talking. And then the user says this. And then let me move this out of the way. And then you again signpost to the LLM with like tokens words it would never ever see in a sequence other than to demonstrate this effect. Okay, we're done with the human, end of turn. The human's turn is done. Now it's the assistant's turn. And we're gonna like use the most random, honestly, like tokens and words to signpost this. And then say, okay, this is the assistant's turn. And if you wanted to see a conversation, multi-turn conversation, um, it would just be this going back and forth. So maybe there would be a follow-up question. I don't know if this is going to come up, but that's actually how the LLM becomes conversational. And then when you ask your question, under the hood, what OpenAI is doing, what Google is doing, what all these guys are doing is actually formatting your question like this to the LLM and basically putting it with these tags. Okay, user explicitly asking LLM, it's your turn now to answer. Might seem weird, but this is how it's done. This is kind of the guts of it. Okay, data set aside, which we can spend a lot of time on, we can then create this trainer class to actually like, facilitate the training. This is nice because it's like a very straightforward, high-level interface. Under the hood, if you are familiar with PyTorch, uh, you might have more control and flexibility with PyTorch, but it'll take more implementation effort. Here we can just specify a bunch of parameters. We don't need to get into the details of it. It's kind of set up for us. But we're just saying, hey, model, I want you to train on this data set for maybe this many steps or this many epochs and with some other parameters. And then, right now this is just processing. We'll let it do its thing. Here we're also kind of showing the kind of guts of what's going on behind the scenes. I won't get into it right now since we're already a little tight on time. Once that's done, once this processing is done, we can actually just do trainer.train, which I'll queue up, and we'll see the training progress go on throughout the workshop. Once that's done, you can actually do inference with this model that you again are holding locally, chat with it, ask it questions. You could even stream, which we'll see. Let's see how we're doing on this progress. Yeah, maybe I should have subset the data, but oh well. Okay, let me just take a quick peek at some QA. Yeah, I think somebody asked, yeah, so the base of LLM is to generate token by token text rather than focus on automating complex tasks. Exactly. And again, it's even for me where this is kind of becoming something I'm more familiar with or has become something I'm more familiar with. It really is like a testament to the amazing technology of where we're at with natural language processing, with AI, with machine learning, that this works so well with this simple goal. Now, there's more things that have been added other than just next token prediction, but that's basically it. Like, if you've ever heard the term autoregressive transformer, maybe I can give a bit of a workthrough of like how an LLM works. Maybe the input will be something like, hello, how are you? Well, let's just say this, hello, how are you? This input goes into the LLM, is processed as a sequence. LLM simply has to predict next token. LLM might predict you. Okay. And then it'll keep going actually. So now if we wanted to keep generating, if we want the LLM to continue generating, the input becomes, hello, how are you? So this is where the autoregressive part comes in. Then again, we feed this into the LLM and ask for the next token prediction. And then continue until some stop sequence. That's kind of it. If you really think about it and take a step back, what an LLM really is, it's a classifier. And what it classifies is of the And what you'll see in these models, there's actually tens of thousands of tokens that these LLMs know. Of these, let's just call it 100,000 available tokens in our vocabulary that the LLM knows. Please predict which one should come next. And then we take the top prediction, or not always the top. You can do some interesting stuff. And that's it. And if we're just doing inference, well, if we're training, what we'll say is, hey, was that prediction, because when we're training, we have a ground truth. We know what it should be. Was that accurate? If it was, okay, again, we do back propagation. We update the parameters. In inference, when you're just chatting with it and there's no ground truth, we just want it to continue, then, okay, you take that top token, let's go again. What should come next now, based on everything that came before? This is kind of the magic going on behind the scenes. Now that we've kind of set up the magic, I think the natural questions that follow is like, how does this work? Because for me, like it's crazy that this works so well. By the way, I'm gonna set this up. Okay, so our trainer is set up. This example, by the way, is just showing you how masking is working. We don't need to get into it, but when we do fine tuning, we're doing some masking. Not important right now. Let's kick off training. This might go out of memory, right? Even though it can fit on this GPU, sometimes, if the batch size is too large, blah, 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 we might go out of memory. Let's see what happened here. Then I'll return a loss from the inputs. Did I make a bug, or did I add a bug somewhere? Dataset text field. So this is because I've seen this before. The model did not return a loss from the input. Some of the following keys for reference received are. I think our data set is malformed. Training data set. Do we need val data set? Well, okay, so be it. I think this is kind of the thing with using open source tools. They update a lot. So in like the couple of weeks since maybe I've used Onslaught last, they're always updating the library. So if you just take the latest thing that they've pushed into the repo, it might not be backward compatible. So code that you ran before, if you're now using an updated version of this library, may break, which is basically what we're seeing. But it's okay. That's not the biggest deal in the world. What this was just going to show is, the actual training process. And then hopefully we can still do inference because, the model is still in memory. Okay, so at least we can still do inference. And because we know the base model is quite strong, it's working out. We've simply asked like, continue the Fibonacci sequence, 1, 1, 2, blah, 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 from 8. And it's continuing. Actually, it's saying the Fibonacci sequence is, so on and so on and so on. We could say continue the next 5 items of this Fibonacci sequence, and it should not, it should follow the instructions and not include the original sequence in the question. Okay, here it's actually trying to be quite like verbose and helpful. Oh wow, it's really trying to explain its chain of thought here. And if you see the reason it stopped, you might be asking, why did it stop? I've given generation parameters, one of them being max new tokens, and it hit the token limit. So it just stops. If I increase this, we should see it again continue and actually reach completion. And just like you're used to with LLMs, if I want to prompt this to be a bit more concise, we can do that as well. But this is great. I mean, you have in memory, this model is, I think, more capable than GPT 3.5, right? Like the original Chat GPT when it came out. And now you can basically just load this in memory and play with it as you want. So pretty cool. Now to go to the fundamentals. Okay. How did we get here? Book related to this topic. Great question. I actually recommend, and part of what would be in the course is there's a series of YouTube videos from Andrej Karpathy. Andrej Karpathy is like one of the godfathers of this field. He's arguably the best teacher of all things related to deep learning in the world. And he makes amazing YouTube videos, like let's say making GPT-2 from scratch. And it's like a 2 hour long video. He also has zero to hero courses and notebooks. I also know places like Stanford and MIT have a lot of just open source material and videos of them walking through these concepts. Now, it'll take a lot of repetition for these things to make sense and to start being a part of your intuition. But, we start somewhere and there's like fantastic teachers out there. I think the first, and what I'll really focus on, since we won't have time to really get into the details of all of this, is an understanding of, the building blocks to LLMs. I really want to get into embeddings and attention, because that's kind of the key part of the engine that lets all of this work. So this notebook should be runnable. It actually is, this is in memory for me right now. And let's just quickly review, understanding of tokens and embeddings. Might be review material for some of you, might be new for not. Let's just cover it. So these LLMs work on tokenization, which is really the process of breaking down words as we humans understand them into smaller components like tokens. So a token could be a word, it could be a subword, it could be a character, it could be some combination of that. And really, the process of doing this tokenization is varied. There's different tokenizers out there that do this slightly differently, but just know, if you just think about it as words and characters, that's probably good enough. So it's a crucial first step, because again, these models don't interpret text. Models interpret numbers. Models and computers just know numbers. So we need a way to turn text into numbers and to turn numbers into text. That's really what an LLM does. We have one that we're loading here, which is like BERT base uncased, which is like a kind of famous BERT NLP deep learning model, which will show us how this kind of conversion is done. Let's take a look at this before we keep jumping in. So we should just be able to run this. And I have my tokenizer. I have my tokenizer in memory, and I also have, this is a model too, right? Like I can again just kind of display some details about it in memory. This is a model that has certain layers that they're doing something NLP related. This is actually an embedding model, which we shall see. Let's say we take some random input sequence. Transformers are wonderful, groundbreaking models. Okay, we ran that through the tokenizer. And this actually lets us see that we've mapped, and just to make this a little bit nicer, this sequence has actually become a series of token IDs. Token ID 101, 19,081, so on and so on and so on. And we can actually make this mapping, a bit more explicit. We've broken down this sequence of transformers are wonderful, groundbreaking models, and we've mapped basically each word to a different token, but also, the punctuation too. A comma is a separate token. This dash, we've actually turned ground to dash breaking into 3 separate tokens. Model to final punctuation, And then typically what most tokenizers do is they have a special designated token to indicate the start and stop, the start and end of a sequence, which we're basically seeing here. Let me just do a quick sanity check on the QA. I'm seeing a question which is great. Um, I've seen some tools that use LLMs to do actions on a device. An example was to open a browser and input a specific URL and do some stuff on that page. Yeah, so we've gotten to the point where it's still GPT and all of that are autoregressive transformers at the end of the day, but that's kind of like saying that's the engine. The autoregressive transformer is the engine. Uh, GPT that you use in your browser, like 4.0, or somebody talked about the demo that basically accesses your computer and does stuff with your browser and whatnot. Uh, these are like cars. So you take the engine, the building block, but you add features onto it. What you might want to think is like tool usage. So you can actually get an LLM because they just seem to understand, like they have a pretty good understanding of reality, text, to know how to call functions. So let's say you've defined, hey, LLM, I want you to solve some problem. You have these functions and tools at your disposal. Use them as you see fit. And they've actually been trained so well, like with such high quality data and really attention to detail, technology and everything, that they're pretty good at knowing how to use these tools to solve a given problem. It's kind of mind-blowing, but they're still at the end of the day doing next token prediction. It's just very intelligent next token prediction. The example of being able to use a browser. So these now we're getting to the topic of multimodal LLMs. So you wouldn't call them large language models, you just call them large multimodal models. Other things can be represented as a sequence, right? Like images can be represented as, or can at least be fed into an LLM to understand images, to understand, let's say, this screenshot of this screen. Where should I click? Where is the URL? What would you call this? Yeah, where's the browser button, whatever this is called, browser field. It's actually able to identify this and then continuously figure out what's the next thing it should do, which is now take advantage, like control some function to go and click this, paste some URL that is determined it should paste. I mean, again, it's amazing that they can do this, but we're looking at the fundamental engine under the hood that lets all of this happen. There's some interesting, if you guys have like heard of system 1 and system 2 thinking, that's how and I think a lot of experts are talking about this whole process. System 1 and system 2 thinking comes from like a really famous book called Thinking Fast and Slow from Daniel Kahneman. He like won a Nobel Prize for it. But basically saying your mind has two modes of thinking. One that is fast and one that is slow. Your fast one you would use if somebody asks you, like, what is 5 plus 5 or 5 plus 6? And you kind of immediately know it's 11. Or when you're just kind of passively existing in the world, like if you're an experienced driver, you're not thinking very hard when you're driving. You just kind of know what should come next. The other system, the slow thinking one, is where you really are like using that brain power to deliberately think about a problem. And you might use that if I ask you what is 21 times 32. If I ask you 21 times 32, now you got to keep a running chain of thought in your head. What is this? What is this? What is this? If somebody asks you a tough question, you need to think about it. You need to think about it. The way I kind of see it with LLMs is LLMs are basically the fast, I believe it's the system 1 approach of just like do the next thing. Like what's the next word that comes into your mind, like, based on everything I've learned before. if you're following the like AI space, you know that GPT has released these models like O1 and O3, which are taking advantage of this paradigm called test time compute. So if you've used them, you know they're like thinking. So they've actually found a way to use this and think about it for us. Like at the end of the day, what are we doing? We're generating ideas and words that come next, but we're smart when we need to think, and we're kind of keeping a running list of thoughts, evaluating, oh, was that the right chain of thought? No, I actually need to do this approach and to do this approach. We're kind of teaching LLMs to do the same thing. So all this to say, it's really interesting that I think these these LLMs as we know them now are the fast approach, but we're quickly developing the slow thinking ones that are branching out into different chain of thoughts, evaluating them, and then converging on the one that it has deemed is good, just like we do, and then finally speaking that good thought. All of that is happening behind the scenes, just like it happens in our head, which I find pretty fascinating. But okay, I digress. Let's go back into a bit of reality here. Uh, Tokenization. I think we have the demo here. You might have seen, by the way, there's like this, what the heck is a tensor? If you're familiar with deep learning, you know all about this. If not, don't worry about it. It's basically a data structure that is really useful for deep learning because it helps us do computation on GPUs. Like this is why GPUs and NVIDIA and all of these guys are so successful these days. It's all about parallelization to make this stuff work fast and intelligent optimization. If you had GPUs, you could get that optimization. We don't. That's basically what we're showing here. In the other notebook, you do. So actually, if I ran this in the other notebook, it would show true. This notebook, we're not connected to a runtime with the GPU. Fine, just showing it. Okay, embeddings. Well, we have a bit of time because I think this is the core concept. Like really the field of NLP, the backbone is embeddings, which is the idea of representation. How do you represent a word? How do you represent a sequence of words? Or how do you represent anything that, let's say, image, like a picture? How do I intelligently represent that? And embedding models themselves are trained. They're their own neural networks. And we would probably have a whole class on understanding representation learning, which is how embeddings work, but embeddings are used everywhere. You can think of it as a form of either dimensionality increase or dimensionality reduction, but they're fundamental to all of NLP. They're a way of converting words or tokens into a fixed length vector of numbers that somehow capture the semantic meaning of the word. Okay, let's just stop there and let's just show an example. Okay, I'm actually just going to copy this into another cell so we can go one at a time. I'm going to take the word dog, pass it through my model, and we can get an idea of the actual representation of the word dog in this model. And actually, maybe we can see the shape. So essentially, we've somehow mapped this word to, and let's focus on this part, to something with 768 dimensions. That's actually the embedding dimension of this model. And you can think about that with all embedders. They've now go from a word, which is, okay, a token, to some representation of a fixed length vector, 768 in this case. These are all numbers. And that means something, or it should mean something. And you can think about, just to kind of flash this, what should a good embedding model do? Like if we want to capture the meaning of words and numbers, what are some objectives we want? One thing you might have in mind is this is a way to capture meaning. And now we're somehow turning words into points in some space. We can't imagine 768 dimensions, so just imagine three. You're somehow taking a word and plucking it in a three-dimensional space, like a 3D grid. In that grid, similar words should have similar vector representations. Basically, similar words should be close to each other in this space. Dissimilar words should be far from each other in this space. So for example, dog and cat should be closer than dog and car. At least that's what I would expect. So just to kind of bring this example back, what I'm doing here is getting the embedding for dog and cat, and then computing the distance between them. So the distance is, okay, there's some unit of 9.63. If I check between dog and car, I would expect these are further apart. This distance should be larger. And it is. So, and we know that this embedding model is somewhat capable. You could try other things like dog and I don't know, something random. Well, ideally dog and dog, they should be no distance apart. So we see that they like completely overlap. I might run into dimension issues here if I do dogs. But even dog and dogs have some separation, right? Another thing that's interesting is like queen and king. Now, because this is a multi-dimensional space, I mean, these things can differ in a lot of ways. There's like this classic example of queen and king and boy and girl. Like you would imagine something, if you took these vectors, if you subtracted king from queen, you get some vector. Should be very similar to something like woman and man. It might seem weird if you're not familiar with this, but what these models are doing is breaking down the meaning of a word and trying to represent it across a lot of different dimensions, extracting information about this entity. Okay, we'll continue on in this. Let's go back to our original input sequence, which was just for reference. Transformers are wonderful, groundbreaking models. Okay, this was just a toy example. We are going to get the embeddings of this sequence. And I'm just printing out some information. So we know that the inputs was 11 tokens. And now we're seeing that the embeddings, by the way, this first dimension is always example. So we only have one example, like that sentence, because you could pass in multiple sentences as a list. This is the dimension of the number of examples. This is the dimension of the number of, the second one is the number of elements in an example. And then the third is the shape of each element. So let's jump into that one. We've created the embeddings for that input. And again, just showing the shape. This is going to print out a lot. But let's go for it. Okay. Let's look at the word transformers. It has a token ID 19081, which actually maps to, has produced the following embedding with these values. This is it. This is how our BERT model is choosing to represent, I can't highlight, is choosing to represent the word transformers. It has learned this, but we don't need to focus too much on that right now, but keep that in your mind. One thing you could do in a well-trained embedding model is actually do principal component analysis to do dimensionality reduction. So we can't visualize 768 dimensions, at least I don't know if you can. If you can, let me know. That would be very interesting. But generally, we do PCA to kind of compress this into 2 dimensions. And at least we can visualize 2 dimensions. And this gives you a rough idea of how close these words are to each other. And you can see punctuations typically far apart, transformer in these 2 principal component dimensions. Again, just trying to represent squish 768 into 2. And we see the rest of the worlds or the rest of the words are quite similar in vector representation, embedding representation. And it's cool that ground, breaking, and dash are very close to each other, as you would hope, because they're kind of representing what a good embedding model should do. It cares about the sequence. They're representing the same thing. Ground breaking really represents one thing, even though standalone, if I just looked at the word ground, is completely different meaning than groundbreaking. That's also kind of the beauty of embedding models. And you'll also see the next part here, self-attention. Now it's already 1 p.m., so I'm unfortunately not going to have too much time to do this justice. Da, da, da. I know there's a lot of questions and I would love to get to them just in the sake of trying to cover material. I do just want to quickly talk about self-attention because it's about, this is like the #1 concept of these LLMs and transformers. We know, and in this example, like words, the meaning of a word actually is dependent on the surrounding words. For example, ground. Ground can mean a lot of things. Ground can mean when you ground an electricity supply. It could mean when you ground your child. It could mean the ground beneath your feet. Or when chained with other words, it has a different meaning in ground breaking. So you can't correctly represent ground as a vector without incorporating surrounding words to help define its meaning. That's like the core concept of attention and self-attention, right? It allows transformers to relate different words in a sequence to one another. And not just, you can extend across large distances. That's why these LLMs are seemingly able to understand and remember things, incorporate things, pay attention to things thousands of words ago that you might have said. The key kind of concept here is also just being able to represent a word in embeddings of like key, query, and value. We use these to actually just mathematically compute how which words in the sequence should be attended to. Let's just go through an example. We're not going to have too much time, unfortunately. Typically, these key, query, and value embeddings are learned. When you train the model, it's learned what these should be. Like these are one of the parameters you can train. Right now, we're not going to do that, so we're just going to trivially, for the sake of having an example, just set them all to be the original embeddings. And what we're essentially computing here is the attention score, which, just for context, like what you typically do, again, each word has key query value. You compute a dot product, which is like a similarity metric between a word's query and key. And this basically tells you how much should that a given word pay attention to another word based on the dot product. Then you have value, which, okay, now you kind of have a scaling factor. Attention tells you how much to pay. Now let's just walk through this. Again, this ideally is like a whole 1 hour at least session. But let's look at our attention weights. Actually, let's look at our scores. We can do dot shape. Okay. How to interpret this? We know we have 11 words in our original sequence. I think it was random text. Oh, it's because it's words. Let's do inputs. Did I overwrite that? I may have overwritten inputs. It doesn't matter. We have 11 tokens in our sequence. What this score is showing is for a given, and we can jump down here. Let's look at the attention score of the fifth word, which is delimited, like we're gonna, with indexing liquid for. This is basically saying how much should the fifth word in our sequence pay attention to all the other words in the sequence. And it's some score. And if I look through it, there's some low values and some high values. So the fifth word in our sequence, for example, just eyeballing this, should pay a lot of attention to the 0, 1, 2, 3, 4, oh, 1, 2, 3, 4, the fifth word in the sequence, aka itself. And it should pay very little attention to the second last and last words in the sequence, and the second word in this sequence. That's what this is showing. What we do is just for numerical stability, we want these scores to actually kind of represent a probability. So we apply a softmax, which basically makes sure that all these numbers add up to 1. It's just a way of transforming all these numbers to add up to 1. And I'm just going to quickly wrap this up. I know we're kind of over time. We run that here. We see that by far the largest value is 88, corresponding to this weight here. And honestly, just skipping ahead because I just want to show this. Okay, this is kind of where it gets interesting. This is the last thing I'll flash. Again, we're a little short on time, so I apologize for that. But you can actually visualize how much each word should pay attention to all the other words in the sequence. How much should transformers pay attention to transformers, are wonderful, dash, or comma, groundbreaking, so on and so on. How much attention should wonderful pay to all the other words? And you see like there's a bit of a heat map. And they're saying to pay attention to themselves the most. Again, we didn't use like correctly trained key query values, but it's still interesting to think about. So when you do more LLM development, it's always interesting to look at these relationships. And it's kind of telling you the dependency of one word in a sequence to all the other words. And we can do nice ways of visualization. So I'm going to leave it there. We're a little bit at time right now. Hopefully this was helpful. I can't see other questions. Hopefully this was helpful, just coming away with like understanding how models are trained, actually being able to do one yourself and play around with this yourself in a notebook. And then a little bit of a flash of the fundamentals behind this technology, transformers, NLP, and all of that. With that, I mean, that's the end of the workshop. I'll stick around and I just want to answer a few questions for a few minutes, but feel free to copy the notebook, try this on your own, and hopefully that was helpful. So that's a bit of a fire hose approach. I think 12 weeks is more reasonable to properly go and explain all of this, but hopefully that at least sparked some curiosity. And thank you all for sticking through. But I'm seeing a question, would it be feasible to develop an LLM tailored to each of our project applications? I'd say it is feasible. Like you can really, based on the training data you use for your LLM, you can tailor it to different use cases. The beauty of LLMs is they're also able to they're able to generalize across use cases. But you might just need one LLM for all your use cases, right? If you need it for ETL into a data warehouse, I'm pretty confident something like a GPT-4o will excel at being able to use tools and kind of automate some ETL for your use case. The reality is how good it is will be up to you actually implementing and experimenting and evaluating it. That's kind of the core of the Gen AI industry right now. We know that LLMs and these Gen AI tools are super powerful, but how do we get them to do specific workflows? If you've heard of agents, that's a big thing right now. Agents basically allowing LLMs to define themselves. What function should I use? What code should I use? What in general should I do to complete some high-level task? Part of that can be actually talking to other LLMs. There's some really cool demos on agents. So most used model, I mean, Meta's Llama is the probably #1 open weight model out there. You can take it and tune it for your purposes. If you don't need to tune it for your purposes, then ChatGPT, OpenAI is probably the most common. But people still use a lot of Gemini and a lot of Anthropic's Claude. So those are still really great models. There's like a ton of really great models out there. Someone asked, I work with data from life sciences, TW. Are there embeddings that can identify that these are different? Definitely. This would be like, now here's the question. Can you do this? Yes. Does it already exist? I don't know. But this is basically exactly what the goal of embeddings is. Just based on strings, you have to teach it how to identify what is similar and what is not. I'd be curious to know in the literature what is out there. There's a lot of work in life sciences and LLMs. So I would be surprised if there's not something already out there. Somebody also asked, where is it? Playing around with king and queen and embeddings, isn't the distance of 8.91 high? Yes and no. I mean, this is a large dimensional space. These words are not exactly the same. So all we're seeing is, hey, they're kind of far apart by some arbitrary metric. But they're actually still closer than most other words. And typically, I mean, what you might expect is maybe king and queen, maybe king and something else, like even kings or some other combination would be even closer. Distance would be, I mean, let's look at this two-dimensional example. This is how everyone always does it. You look at a 2D or a 3D, and then you tell yourself 768 dimensions. How far apart is, let's say, oh gosh, transformers and CLS? What you do is you compute the Euclidean distance. So this is simple. We know this, two-dimensional, x, y. You take the x coordinates of these 2 points and you subtract them and you square them. And you take the y coordinates, you subtract them and you square them. You sum that all up, then you take the square root. Actually, you don't even need to take the square root. Anyway, that's your distance. That's like a Euclidean typical distance. There's other ways actually to compute distance metrics. Like cosine similarity is one, which again, you can imagine what is the angle of these points relative to the origin. So you might say the angle here is like 5 degrees. And then the angle of CLS is 7 degrees. So actually, based on angles, they're quite, and what is the angle between them? That's really the key part. What is the angle between transformers and CLS? It's actually quite small, which means they're quite close to each other. That's another way to kind of capture how similar, how close are these things to each other. Why did that do that? Yeah, I think that's a fair, like, this is how far apart they are. That's what that distance means in some n-dimensional space. We know three-dimensional space, we cannot, you just can't imagine a space bigger, but it's out there. It exists. All the math scales to as many dimensions as you want. Are agents the same as being agentic? Yeah, basically. Like agentic framework is just things that use agents. It would be something I want to cover in the full course too. Very, very cool. I think we as an industry are still figuring out like exactly how to use these and how to make them reliable as best we can. But that will be the future, like more and more agents, more and more agentic things. It's already here, but just more of it uh, is what we're going towards. Okay, awesome. Hopefully, I helped answer some questions at the end here. Thanks again, everyone, for sticking around. Great questions. Um, Feel free to go through the notebook. Hope it helped, and have a good weekend. Take care. Bye bye.